All right, we're going to enter our last topic of study in AP calculus. So this is pretty exciting. Um, we are going to be studying in our last topic differential equations. And the topic, differential equations, well, it's self-explanatory. It's equations with derivatives. So anytime you have an equation, for example, dy dx equals x, this is a differential equation. Now, we've actually been dealing with this. This just says the derivative equals x. Uh, but a differential equation is an equation that has a derivative in it. And what we're going to be leading to is trying to solve differential equations. Now, this example that I gave you already, this is something that you know how to solve already. I mean, you could integrate both sides. And when you integrate both sides, we get y equals 1 half x squared plus c. So you know how to solve differential equations, or at least some of them, but they'll get a little bit trickier. So here are some more examples of differential equations, and we notice that they start getting trickier when they're not in terms of x. So all of these have y's in them. Uh, this has a y in them. So some of them you can solve. We could solve this one. That gets us y equals a constant. And we can solve this one. And we know that that gets us y equals arctan. But these other differential equations we don't know how we do not yet know how to solve. Um, Now, there are two very special differential equations that we're going to be talking about. The first one is called a first order, and it's called a first order because the derivative equals the function itself. So the derivative is the same thing as the function. And the second order differential equation is when the second derivative equals negative the function. So we'll look at these now. So can anyone think of a first order, I should say, differential equation? And in college, there's a course on differential equations, and it's called diff EQ. That's what all the math majors will call it. So what function and its derivative are the same? You know this, right? Well, an example of a first order differential equation would be this. Y equals some constant times e to the x. Because what's the derivative of this? Well, the derivative is the constant times e to the x. Right? We know that. The derivative of e to the x is just e to the x, and a constant stays there. So here is an example. This is a first order differential equation where the derivative equals the function itself. So anytime you get to this first order differential equation, you know that the solution is going to be y equals c e to the x. This is the solution to a first order differential equation. And here are all of the potential graphs for varying levels of C. So as C gets smaller and smaller and smaller, our graphs are getting wider and wider and wider. And for these blue values, my C is negative, so it's been reflected over the x-axis. But here are a family of curves for varying values of C. And all of these curves are solutions to our first order differential equation. What about a second order differential equation? Can anybody think about that? When you take the derivative twice, you get the negative value back. What could that be? What could that be? Well, I'll give you a hint. Let's say y equals sine. Well, then my derivative would be cosine, and my second derivative is negative sine. Oh, well, if I make this negative and this negative, now we've created a solution to a second order differential equation. So whenever you have a second order differential, we will be using sine or cosine as our solution. But we'll get to this a little bit later. This section, the purpose of this section is for us to just um, validate that certain functions are in fact differential equations and to do some very simple solving of differential equations. So for example, in this first problem it says find a function that satisfies both the differential equation given and the initial condition that y0 equals 1. Well, because there's no y's in this, it's just a straight up integration problem. We have dy dx equals 2x over x squared plus 1. So to solve it, I'm going to integrate both sides. When I integrate both sides, I get y equals ln of x squared plus 1 plus c. And so let me stop. Before we incorporate this piece of information, this plus c gives us a family of curves. And so here we have all of these different functions for varying values of c. But if I use this initial condition, when x equals 0, y equals 1, so I can put 1 in, I get ln of 1 plus c. And we know that ln of 1 is just 0. So this tells us that c equals 1. So therefore, my equation is y equals ln of x squared plus 1, absolute value, plus 1. Okay, so that was solving a differential equation, and hopefully that you see we've been doing that already. But now, what we're going to do is we're going to show that for any constant c, that this is a solution, that's a solution to this differential equation. Well, how are we going to do that? What we're going to do is we're going to say, okay, let's take this solution and let's find its derivative. So when we do, we get y prime equals 2x over 3, and then the derivative of c over x, well, we could rewrite c over x like that, and we see that the derivative is negative c over x squared. All right, so this is what y prime is, and we need to show that this is the same as that. Well, does it look like that? Not yet, but we can do some work on my differential equation. Let's solve this for y prime. So we get y prime equals x squared minus y over x. Well, that's x minus y over x. And then if we substitute what we're saying y equals, this value right here, we get y prime equals x minus x squared over 3 minus c over x all over x. And that simplifies to x minus x over 3 minus c over x squared. Just distributing that x to here and to here. And this simplifies to 2x over 3 minus c over x squared, which is exactly the same thing that we had here. So how do we verify that? Well, we took what they're telling us is the solution, and we found the derivative. There's the derivative. Then we took the differential equation that we were having to solve, set it to the derivative. We solved it for y prime, and we wanted to show that this equaled that. But we had to make an intermediary step and plug in. We had to get rid of this y, and so what we did is we substituted this value of y in for it. And when we did that and did some solution, we saw that the derivative, this derivative, y prime, is the same as the derivative of this function. So therefore, this boxed in is a solution to this differential equation. Let's do more of that. So it says, show that this equation satisfies the logistic differential equation given here. Okay, so what we need to do is we need to take this derivative, take a derivative of this function, and show that it equals the derivative function. So we get y prime equals low d high minus high d low all over low squared. Well, simplifying this, we get e to the negative t all over 1 plus e to the negative t squared. And that's what y prime is. So now we need to show that when we take the derivative, sorry, when we sort of evaluate the original differential equation, plugging in this in for y, that we get the same thing back. Let me pause and say this, and this is an important pause. This section is an introduction to differential equations. So we're just showing you, here's a differential equation. I'm telling you this is the solution. Verify it. This is kind of an ugly just beginning. Where we're going in the next couple of days is for you to get this, have this differential equation, and actually solve it to figure out what is, given this equation, differential equation, you'll be actually able to get to here. That's where we're going. But for now, what we're going to do is we're going to take this dy dt and substitute those values of y in. So 1 over 1 plus e to the negative t times 1 minus 1 over 1 plus e to the negative t. And what we're going to do now is we're going to simplify this a little bit. So we're going to get this over a common denominator. So that's 1 over 1 plus e to the minus t, 1 plus e to the minus t over 1 plus e to the minus t, that's just 1, minus 1 over So this is just a good practice in geometry, or sorry, in algebra, in terms of rearranging equations and doing an algebraic proof. So now if we combine these terms, we get inside the parentheses is just e to the minus t over 1 plus e to the minus t. And when we multiply, we get exactly back, or we get the exact same thing back as we had up here. And that confirms that this is a solution to this differential equation. All right, a little bit more. Show that the following is a solution to this differential equation. Okay, well, we know what to do here. We have y prime equals, the derivative of that is negative c over x squared. And over here, we have that y prime equals negative y over x. Well, y, substituting c over x in for y, we get negative c over x, which is just negative c over x squared. Exactly the same thing as we had here. Therefore, this is a solution to this differential equation. We're not going to do B. Okay, so some more examples. We want to show this is a solution to that. We're not going to do B and C. We can play with that in class, or play with that, as you're doing your problems. So if we want to show that this is a solution to this differential equation, we know what to do here. So we take the derivative. We have y prime equals c e to the x minus 1. And over here, we have y prime equals x plus y. Well, we know that y equals the following. So let's put that in for y. So we have c e to the x minus 1. And so these are going to go away. And we get that y prime equals c e to the x minus 1. This is kind of like geometric proofs where you're just, you're given two things and you need to show that they are the same thing. But it's introducing the idea again that, we have an equation that has a differential in it, a derivative in it, and then an equation that doesn't, and we want to show that, the equation that doesn't have a derivative is a solution to the differential equation. Okay, so now, earlier on we verified that this was a solution to the following differential equation. Now let's say, now we want to find the c given some condition. So if you're given a condition, you can solve for c. Well, it's just as easy as you think it might be. You put the y in for y and the x in for x, and you get negative 2/3. So we're going into this solution. So negative 2/3 equals 1 squared over 3 plus c over 1. And when we solve this, we get that c equals -1. So that is our constant c. So therefore, the equation y equals x squared over 3 plus -1 over x is a solution to this differential equation, and it goes through that point. Okay, so now let's do both steps together. Let's find a, or let's show that um, this is a solution to the following differential equation, and then let's find the exact solution for it to meet some condition. So in part A, we know that y prime would equal 3a x squared, and we want to show that that equals to this, where y prime equals 3 times y. Well, y is ax cubed, so 3 times ax cubed over x equals 3a x squared. The same thing I had over here. Good. Um, so now we want to find the specific solution that has this condition. So we're going to say, well, plug 2 in for y and -3 in for x, and we're going to get 2 equals a times -3 cubed. So we get that a equals -2 over 27. So therefore my final solution is that y equals -2 over 27 x cubed. All right, last example here. We want to show that this is a solution to our differential equation. Same steps. Take the derivative. So derivative of e to a function is e to the function times the derivative of the function, so -2x. And that should, we want to show that that derivative is the same as this derivative. So we have y prime equals -2x times y, where this is my y value. So plugging that in, we have e c minus x squared. And these are exactly the same thing. So it's a solution. In B, we want to find C. We want to find a solution. So find C that satisfies this initial condition. So that initial condition says that when x equals 0, y equals e. So we can say e equals e to the c minus 0 squared. So therefore, c must equal 1. So our general solution, sorry, our specific solution to this differential equation, meeting this initial condition, would be y equals e to the 1 minus x squared.